Hello everyone. So this is the CSD project presentation of our team 2. So we can see first the physical things. So this is the monitor, and we have that connected to HDMI port to this IPO board, and then it's powered by the cable. So one is for the monitor and one is for this IPO board, two adapters, and we can see the keyboard is connected through PS2 port to my laptop. So actually the keyboard requires 5 volts, so which is not provided by this IPO. So we are powering the keyboard with my laptop, but we'll be extracting those signals to receive to actually decode the keyboard signals. So you can see there are one HDMI port, the power cable, and one is the JTAG programming cable, another one is the keyboard. Okay, now we will see how to actually use the computer. So we can see the monitor, keyboard, everything is plugged up. So the only thing is remaining is to load the OS into the, along with the processor, into the Java board. So to do that, what we'll do is we'll just click program device here. So this computer is actually running Vivado. So Vivado has this option to actually load bitstream to Java board. So we'll just click program. So as soon as we program, we can see the monitor, the OS, the process running, and it's pointed to the first instruction of the OS. So initially the OS actually displays hello world. So this is the thing that the OS displays first. So we can see that the OS is perfectly booted. Now what we can do is we can remove this JTAG programming cable. We no longer need that. So we can see now we can see, if you see the Java board, there are only 3 connections. One is the power, the other one is the HDMI, and the third one is the keyboard input. So now this is a standalone computer. You can just use it like any other computer from now. So the thing is, the Java board doesn't have a hard disk, which means that we have to boot the computer every time we switch it on. That's why we use JTAG programming every time we switch on the computer. Now once the computer is loaded, we'll just press enter. So this is the shell of the OS. Now we can see that this is like any other shell. The way how to use this shell is simple. So we know ls command in Linux. So okay, so you can see like once you press ls, you can see all the commands that you can use in our computer. So to use Fibo, you just type. So it will just ask for a number to enter. Let me enter 15. So the 15th figure of the number is 987. So just like any C program that you can use, let me run the prime number command. So it will ask us to enter a number. Let's say 97. So 97 is a prime number. Likewise, you can again call it with other input. 100 is not a prime number. So this is just like any other programs. You can also use clear to clear the screen if you want, or else it will automatically clear when once you go down the 30 lines in the screen. Now let's see what all commands we have, other commands we have. So we have quicksort. Let me run quicksort. So enter the number of elements. Let's say 5 elements. Then enter some elements like minus 45, 8, 0, 34, 89. So you can see the numbers are sorted using the quicksort algorithm. Again clear. So we also have tree data structure implemented, the BST. So enter the number of elements. We have like again 5. We'll just enter the numbers like 90 minus 98, 45, 87, 0. So the in-order traversal of the tree. So we can see we know that by BSD, the in-order traversal will result in a sorted array. So you can see the numbers are sorted, and we see this output. Now we also have this. We have also implemented a game in the computer, the regular, like the famous Snake game. You can see in old phones, old Nokia phones. So you can just play the game by just typing Snake and then click enter. So we can see this game is loaded. So just to play the game, we can just use WASD, these 4 buttons, and then you can just operate the snake. So as you keep eating food, just like the normal game, the size of the snake will increase, and once you cross the boundaries, the snake will appear in the other side. Now you will lose the game once you hit yourself. So you can see, once you hit yourself, the game gets completed, and then you will be shown the score that you have achieved. Here we have 18, which was the final length of the snake, and you can just click enter, and you'll return back to the shell. Now you can use the computer as usual without any, just like before. Else you can play these games snake and also use the user programs. So this is the overall demo of our computer. Thank you. Sorry. Okay, so the other thing that we implemented in our computer is the process scheduling. We know that in Linux, we can do multitasking with just one core by just switching processes for like a small quanta of time. So we implemented round-robin scheduling. So I'll just demonstrate the basic working of process scheduling in our computer. So to just do that, I'll be loading a separate bit stream, which is different from what I ran before. So this bit stream actually has these interrupts, which will, so for every half a second, a context switch happens. So whatever process is running, it goes background. The OS comes up front, runs the round robin scheduling algorithm, finds out which program will get chance to execute next, and switches to that program. The OS goes back, and that program will start executing. So this happens for every half a second. So I'll just demonstrate a basic level of that. So I'll just program this ps.bit. So once I program, we can see that. So you can see that right now what's happening is that there are three processes. One is one which prints C continuously, the other one which prints D continuously, and the third one is the shell. So here actually three processes running simultaneously, and each process will get a chance. So when C's chance comes, it prints C. When D's chance comes, it prints D, and when shell's chance comes, it executes the shell. So in a round robin fashion. So, and also we used mutex locks actually to prevent the situation where C prints only half a C, like paints only half a screen, half the letter, and then a context switch happens, and then D comes. So then the D prints the other half. So that situation should not occur. So we used actually mutex locks. We implemented mutex lock in our OS. So what happens is that when whatever process that calls the display function, at the start of the function, a lock is acquired. So that lock will be released only when it completes its execution. So if C acquires the lock first, then D cannot print when its chance comes. So D will wait in a loop, and only when C releases the display function, then D can use that display function again. So here we are demonstrating the use of locks, actually a real life example or real life use case where the locks are actually required. So this prevents us from seeing any half C's, half D's, like half printed things. Now the best thing about this is that we can also use shell simultaneously. As you can see, the screen is overloaded. You can just enter ls. So you can see, even though C's and D's are getting printed, the ls is still working. This because when shell's turn is when shell gets its turn, it acquires this lock when the display lock, and then it prints whatever content it has to print. So we can actually simultaneously use this. We can also use clear. Okay. Since there are printings and everything going on, we should be cautious while entering. So you also see that it's taking a while to actually clear the screen, because the clear function is called by shell, which is getting a very small amount of time, and C and D are also getting the time. So that's why we can see the clearing is happening slow than the usual thing. So actually all the processor will actually get 1/3 of the time when you execute. So this is a sample demonstration of our process scheduling, 3 processes at a time. So that's it. Thank you.